The work I'll present was developed in the framework of Exafoam. As you have heard yesterday from the presentation of Professor Orviazak, it was a big project where a number of entities put together efforts to improve the efficiency of OpenFOAM. And this specific work was done in the group, a cooperation between the group of the University of Minho and the University of Cambridge, specifically Professor Orviazak, regarding the coupled solver for viscoelastic fluids. This is the outline of the presentation. I will briefly describe the governing equations, the problem we have to solve. Then I will show you the coupled approaches we tested, because we tested different approaches to reach our aims. And then I will show you results. And the presentation will end with some conclusions. First of all, the governing equations. And to illustrate the difficulties associated to viscoelastic flows, what you see here are dummy particles that are inside the flow of a complex of a realistic profile extrusion die, an industrial profile extrusion die, and you can see from the colors of the particles are related to the magnitude of stress. And there is a large region of the domain where the particles have low stress, but when the particles start being accelerated, the stress increases. That generates, is related to the properties of the material, and that generates peaks of stress that usually are quite difficult to handle. And you can see, especially in the most restrictive regions of the extrusion die, it's quite difficult to compute the stresses, and the process is complex. In the usual approach, the equations or the equations that govern the process are solved in a decoupled manner. And talking about the equations that must be solved, when the materials are inelastic, so we don't have elasticity, solve the mass conservation and the momentum balance equation using the usual approaches. When we have viscoelasticity, an additional term appears in the governing equations, is the divergence of stress of the stress tensor that stress tensor comes from other equations, because we cannot compute the stress tensor explicitly based on the velocity field. So this is the typical set of equations that must be solved, but this is the general transport equation, and there are a number of models that are available specifically in foam extend to solve viscoelastic fluid flows. In this case, I'm illustrating with the Gizukus, one of the Gizukus model that is the one we have used in this specific work. There are a number of terms from the constitutive model that needs to be discretized, that needs to be treated numerically in order to solve the problem of this complex problem. And in the usual approach, these equations are solved in a segregated manner. And what we aimed at the Exafoam project was to test what would happen if we solve the problem coupled. We try to couple the different equations. Before giving you the details of the approaches we tested, I would like to point out one relevant detail. It's related to these equations. And this one, the last one, the constitutive model, is the equation that governs that transport one mode of the stress tensor. But typically, the material doesn't have, cannot be represented by just one mode. The viscoelastic materials comprise molecules with different lengths, and that induces different relaxation times. And when we try to couple, this is the experimental data. I cannot get into details here, but you need to trust me. This is experimental data we collect regarding materials properties. When we fit that behavior with just one mode, with just one equation, this is the best fit we can get, which is obviously too bad. In order to solve that problem, instead of using just one mode, we have we add additional modes to the equation, to the model. Sorry. For each additional mode we add, we get 6 additional stress unknowns for the problem. And in this case, we are doing it the best fit we get with 2 modes. Okay, I see a few of you saying that's not yet. Okay, if we use 7 modes, we get a good fit for this case. And for this case, I'm illustrating we need 7 modes, and 7 modes are the typical number of modes, or 5 to 7 modes is the typical number of modes we need to fit the behavior of one of the materials we used usually. That means if we have 7 modes, we have 46 unknowns per cell, which is obviously too much. Another important detail, because you'll see some modifications on the governing equations, is that we in order to try to additionally couple velocity and stress, we use the improved both sides diffusion. That was an approach developed a few years ago in order to promote the connection. Again, I will not enter in details here. Regarding the coupled approaches we tested, the first one, we used the coupled solver that is available in FOAMX10. We just grabbed that solver and we added the solver couples velocity and pressure. What you see here in terms of color coding is the different terms that go to the coefficients of every computation of all computational cells, and okay, the process builds in terms of algorithm. The process builds the matrix, solves the problem, the coupled problem, and what we did as what we call the semi-coupled solver was to just add the governing the constitutive model in a decoupled manner, okay? Decoupled from the previous equations. And we did it because we want to test the possibility of getting advantages from this approach, because we anticipated some difficulties when dealing with the large number of variables for the full coupled approach. And the second approach we test, what we call the fully coupled solver. In the fully coupled solver, as I mentioned, we have the stress equation, the momentum equation, and we didn't couple all the modes. We selected one mode, the most relevant mode, to couple the system, to couple the stress and velocity and pressure, And we treated the remaining modes, as illustrated here, we treated the remaining modes as decoupled. Okay? And okay, this is the equation we get from that configuration. And regarding this is the coupling between stress and velocity at the momentum equation. And for the constitutive model, we use a Taylor function approximation of the advection term of stress in order to get an implicit contribution, explicit contribution, and a cross coupling again. We did it, as I mentioned, for one mode. So this is the final coupled matrix we get for each cell. And again, the color coding we have here, the similar to the previous one we had before, but now we added the stress contributions. And as I mentioned, we did it for just one mode, and you see even with that with just one mode the amount of information we have to deal with, and all the remaining were treated in a segregated manner. So, give you an idea of the results we were obtaining. We tested 3 cases. I will show you results of mainly 2 of the cases that are close to the industrial cases, because, as I mentioned in the beginning, the purpose is to be able and to improve our ability to deal with industrial cases. So this is a simple extrusion die, similar to the initial one I showed, but much less complex. In this case, we used we modeled just 1/4 because there are 2 symmetry planes for the calculation. And for this material, we use 6 modes to do the fitting. That means we have 40 unknowns per computational cell. An idea of the mesh we have been using, and after doing several tests, we faced an issue because we were not able to obtain any improvements associated to the calculation, and that was related to the fact we're controlling the convergence through the residuals. But the way the residuals are defined in different approaches are not consistent. So it's not a good approach. We figured out it was not a good approach to do it, and instead of controlling convergence through the residuals, we instead control the convergence through some of the relevant calculation variables, as in this case inlet pressure and the outlet flow distribution in 3 regions. In this case, we divided the outlet cross-section into 3 regions, and we calculated the flow in those regions, and when it was reaching a steady value, we considered the problem converged. And the results are seen here. In this case, we're able to perform calculations up to Courant 5. And for pressure, these are the values we get for the convergence of the flux in zone 3, that was the one that converged later, and for stress, the calculation time, for the semi-coupled approach, that was the one that with which we obtained the best results, with the segregated approach, and with the fully coupled approach. The fully coupled was, in this case, the one most demanding. So it means that the effort that is required to solve the problem due to the larger matrices we have didn't allow us to reduce the calculation time. Anyway, in this case, using the semi-coupled approach, it was possible to obtain a speed up of 2.65. Okay, but the fully coupled was 8% slower than the segregated one. For the most complex case, as the one illustrated here, again, we controlled convergence through the inlet pressure, and we divided the outlet cross-section into 3 zones as well. And we checked for convergence by the division of the flow in those regions. And you can see here the results. Again, the semi-coupled approach allows us to obtain better results, but in this case, the fully coupled was a bit closer. So with we managed to obtain in general a speed up of 2.92 for the semi-coupled approach, but the fully coupled also allowed us a speed up of 2.4. Give you an idea of the memory requirements that are relevant for the for assessment of the algorithms. For the fully coupled or for the fully coupled approach, we need usually 4 to 5 more times memory than the one we need for the segregated approach, which when we increase the number of cells, in this case in B4 we use 20 million cells, when you increase the number of cells, it reaches 2 values quite big. And okay, give you some conclusions of the work. So we managed to deal with the complex cases, and our main goal is to reduce the calculation time. We succeeded on that. For the implementation, it was required to refactor the viscoelastic class in foam extend. We proposed an approach to deal with the multimode rheological models that are required for this kind of problems. And we tested 2 different approaches, fully coupled and semi-coupled. As I mentioned before, the best results were obtained with the semi-coupled approach. We still believe that there are benefits we can obtain from the fully coupled approach that needs to be better explored, either by us or by any of you, because all these codes are available in the repositories of Hexafoam, both the codes and the case studies. So anyone that wants can test them, can grab the codes, explore the case studies, and help us finding us a better solution. Thank you.
Thanks, Robert, for the excellent talk. I think we have time for a couple of questions. Thank you very much for your wonderful presentation. Would you be here to see more details on how programming has been done in terms of the algebra? Would you be able to tell a bit more about how in a semi-complicated and a fully program do you do the
This is an ongoing work, as I mentioned. There are a number of studies that can be done to improve. We have used algebraic multigrid for the fully coupled approach, following the best results we have been obtaining with a coupled solver. We did a few tests, but not more than that. So this is what we use for the fully coupled approach. I agree. We have the time is short, so we cannot explain everything. But hopefully, as I mentioned, everything is public, available. Anyone can download the cases, the configurations, everything we use. Sorry.
Thank you. I have two questions. For the simple scenario where your outlet, well, I understand that the geometry is dictated by the industry, right? By the industrial case that you are trying to solve. But first, you have solved a simplified version of that, right? And I was wondering what outlet, this is my first question, what outlet boundary conditions have you used for that simple problem? If it is zero gradient, how, yeah, go on.
Thank you for the question. Also, no, we didn't use zero gradient for the stress field. We used linear variation. Yeah. Linear variation for the stress field.
So I can imagine that since the outlet is not long enough necessarily.
Yes. The material might not fully relax.
Yeah.
At the end, and the best approach we found. Is obviously not to use zero gradient.
Yeah, yeah.
And we use a linear variation.
Can I ask the keyword in OpenFOAM if I want to use that boundary condition? What's the name of the boundary condition? Do you remember? Maybe it's
no, it's not available. It's,
okay.
It's in the code.
Okay, got it. Okay, and just a general
stress field.
Yeah, just
it was
general
a new implementation.
Yeah,
it's a new.
Thanks. Just a quick general question. Regarding the demand in the market for rheological simulations, some people think that it's actually there is a lot of demand, but a huge lack of knowledge in this area compared to, for example, compressible flows or automotive industry. What do you think about that, as you have been involved in this industrial problem?
Mm-hmm. Yeah, I've been working a lot with industry in this area for a long time. And is exactly what you refer. Mainly due to all these difficulties to solve realistic viscoelastic problems, and these geometries you don't see very often in publications regarding viscoelastic materials. From my experience, they are not used in industry, and the calculation time is one of the issues. And what the consequence of that is, in order to design tools, you have to do additional experimental trial and error in order to adjust the tools. And if we use more realistic models, we would get obviously the benefit from it, and we are targeting that. There are some other additional problems that are not solved here that are also related to viscoelastic behavior.
Thank you.
Well,
thank you for the presentation. So this is a part of Exofoam project, and I was wondering how was the scaling of the solver? How much speed up did you get with how many cores maximum?
I told you it was three times.
Oh, okay, sorry. I missed it.
Around 3 times in the speed up. The speed ups we obtained in this specific problem. But to let you know, the original solvers were not able to get convergence for this specific problem. When you solve viscoelastic problems with very regular meshes, everything you are able to get convergence. When you start using realistic geometries, so we start using meshes, complex meshes, it makes everything more complex.
Of course. And so 3 times speed up compared to the original solver, and
yes.
Right? And then with how many cores and nodes?
In this case, we have used 1,000, around 1,000 cores.
Around 1,000
to get those calculation times.
With 20 million cells.
Yes.
Yeah. Thank you.
20 million cells. So we're talking about a problem with a huge number of degrees of freedom. It depends on the way you define it. Yeah, it's if I didn't check the value at the thinner sections. We can do it, but we should be talking about something around one. Yeah. Yes. Yeah. But I didn't check I'm sorry, just to complement the answer. Usually what you see is, okay, when you have a regular geometry, you can compute the Heisenberg number. But there, if you assume parallel flow between parallel plates, that's maybe to get an approach of. But the worst region is when the material is accelerated. That's when you get peaks of stress due to the elongation of the formation rate.
The signal that we are getting, is it more on the side or ego or
No, it's mainly related to just the coupling the equations. That was the change that was made, and it is assessed here. Yeah, the codes that I mentioned, the codes are available. So the old Viscoelastic classes were refactored in order to deal with this, and the codes are available for download for Viscoelastic flows. Yeah, and there are. We will not see any results of that in this specific conference, but there are also results on that. Everything is in the website. You have the website, the publications, links for the publications, everything is there. And we are working to finish the book. There is a book that will combine all the major contributions from Hexagon.